So in the previous lecture, we had gotten to the stage of defining the creep compliance for a generalized Kelvin-Voight model with 3 elements. And we had defined the creep compliance only up to the creep compliance in Laplace transform space. So let me remind you where we were at. Okay. So recall. Okay, for a generalized Kelvin-Voight model with 3 elements, the creep compliance could be written as follows. So we derived this in the previous lecture as J, and we were still in Laplace transform space, so I'll write J bar of S was equal to 1 over Q3 of S times the quantity A1 over S minus lambda 1 plus A2 over S minus lambda 2 plus A3 over S minus lambda 3. Let's call that equation 1. I'll just by way of reminder remind you that Q3 is a constant. A1, A2, and A3 are all constants, and we actually wrote down what those constants were in the previous lecture, so refer to that if you want to see that. And then lambda 1, lambda 2, and lambda 3 were constants. They were the roots of this third-order polynomial that came out of the solution. Okay, so this is all the non-S terms here are constants. Okay. So this isn't a convenient form for taking the inverse Laplace transform. So let me write why that is. So note the inverse Laplace transform of, let me give you the form. So I'm going to write this as the L inverse Laplace transform of the quantity 1 over S times S plus alpha. The inverse Laplace transform of that is equal to 1 over alpha times 1 minus e to the negative alpha t. Okay, let's call that equation 2. Why is that helpful? Because if I distribute this 1 over Q3 S term throughout this, you'll see that this each term now takes this form, okay, multiplied by some constant. So now we can go ahead and take the inverse Laplace transform of equation 1. So take the inverse Laplace transform of 1. And if we do that now, well, on the left-hand side, the inverse Laplace transform of J bar is just J of t now. I'm going to leave this 1 over Q3 term outside. Okay. And then I'm going to put the S, distribute it through there so I can apply this equation 2. And this first term looks like, let's see here, A1, which is just the constant that comes out. And then obviously I have a plus alpha. That plus alpha is actually a minus lambda 1. So this becomes minus 1 over lambda 1. Okay. And then times the quantity 1 minus e. Remember alpha now being negative lambda 1, so the negatives cancel and I'm left with lambda 1 times t. Okay? Plus the second term will be a2 times negative 1 over lambda 2 times 1 minus e to the lambda 2t, and then plus our third term, which is a3 times negative 1 over lambda 3 times 1 minus e to the lambda 3t. Okay, we'll close the brackets, and we will call that, well, let's go ahead and write it in its more compact form, the sum form. Looks like 1 over Q3 times the sum from I equals 1 to 3 of, I'm going to now multiply this through. This looks like negative A1 over lambda 1, negative A2 over lambda 2, negative A3 over lambda 3. So this is negative AI over lambda I times 1 minus e lambda I t. Okay? Call that equation 3. Okay, something to note about equation 3. Okay? Right, because we know what happens, this is a creep compliance test. So we're applying a stress and we're monitoring the strain. That strain increases monotonically. So what that means is that the exponential terms, they can't go to a negative value. So the lambda values must be less than 1 there. Okay, so because the strains monotonically increase, okay, the exponents must be decreasing functions of t. Okay, functions of t. And what that implies then is that lambda I, all those lambda i's are less than 0. Okay? What we're also going to observe is that you can imagine what the solution would look like if I had n elements, right? There's nothing special. I could have had 2 or 3 or 4 or up to n, but I can look at equation 3 and infer the general solution from it. Okay? I'm going to observe that for n elements, okay, so of this generalized Kelvin-Voight model, so for n elements, our solution procedure would be the same. Okay, be the same, and we would find the following solution, right? That we could write that the creep compliance function j of t is equal to, now instead of q3 it'll be 1 over q sub n for the n elements. We're going to sum then from I equals 1 to n, and then this still looks like negative ai over lambda I times 1 minus e to the lambda I t, where lambda I, remember, is less than 0. And we can call that equation 4. So we're not actually to the final point here, but equation 4 does represent the general solution for the creep compliance for a generalized Kelvin-Voight model. We're going to do a little bit of massaging of equation 4 just by making some observations. So let me remark. So here we go. Remarks about equation 4. The first remark, number 1. We already said that lambda I must be less than 0, but we can observe from the fact that this is in the exponential and this must be a unitless quantity that lambda must have units of 1 over time. So the first observation, so observe that lambda I is must have units, okay, of 1 over time. Okay, so we're going to replace lambda I with some time value. And remember that lambda is negative in this case. So we can say that lambda I is going to be equal to negative 1 over tau sub I. And tau has that definition that we talked about previously. This is the retardation time. So if we use that quantity, then now j of t becomes 1 over q sub n, sum from I equals 1 to n, of now this quantity becomes ai tau I, right? And then this quantity becomes 1 minus e to the negative t over tau I. Okay? Let's call that equation 5. Okay, remark number 2. Okay, we further note that let's bring that qn term inside the sum, and then this quantity becomes ai tau I over qn. Okay, that the quantity ai tau I over q sub n is going to be constant for any value of I, right? Is constant for each I. Okay? So we're going to say that we're going to define now, we'll introduce this idea, we'll call it J sub I is going to be equal to AI tau I over Qn. Okay? And that lets us then write the following. We can now write the creep compliance J of t is equal to now the sum from I equals 1 to n of J sub I times the quantity 1 minus e to the negative t over tau I. Okay? Equation 6. Okay. So again, now we're getting to a fairly general term. What this says is that we need two quantities Ji and tau I for each of the elements to quantify it, or rather to write the expression that we need. Let's go a little further and make the remark that we talked about when we went to a standard linear solid for the Kelvin model. Recall that we want the ability of our generalized model to be able to respond to an instantaneous applied strain, which a Kelvin model can't do because it has that dash pot. So we need to really have this spring component as the first element. Okay, so I'll just say recall from our previous discussions that we would like. So we would like the first element in this model to be a pure spring. A pure spring. Okay, so what's the retardation time for a pure spring so that it can respond to this instantaneous change in strain? Well, it responds instantly, so the retardation time we'll call tau 1 is going to equal 0. Okay, so that's going to let us, if tau 1 equals 0, then this term goes away in the first term and we're left with just a constant. So so what we can write then is that, and I'm doing a little swapping of indexes here. Instead of calling it J1, I'm going to call it J0. Okay, I'm going to shift all my elements. You know, element 1 is now element 0, element 2 is element 1, etc. So J0, which is time independent, plus now the sum from I equals 1 to, we can say to n minus 1 if you want, or we can just say there's n Kelvin-like elements that have a dash pot in them. Okay, so and then we'd still have this same J sub I, 1 minus e to the negative t over tau sub I. Okay, we'll call that equation 7. And all I did is I said where element 1 went to 0, 2 went to 1, etc. And then I just redefined n from n minus 1 to be, just call it n again. Okay? Okay, so this is the form that we like. So let me make a final observation. We want to observe that rather than have to specify E and eta, which are hard quantities to get at, and it really they just represent approximations. Okay, so observe that rather than specifying E and eta for each element, okay, we need to specify Ji and tau I for each element. Okay, and I should subscript these as i's, so EI and eta I. And the reason is, of course, in a real material, the creep compliance is a spectrum. It's not a single relaxation time or a single spring and dash pot. So really, if we say we're going to choose a 3-element model, we're going to do the best we can to fit a 3-element model. We don't have a real way of saying, well, this corresponds to a particular spring value or a particular eta value. And it's actually sometimes more convenient to be able to talk in terms of looking at the creep compliance curve and saying, well, we know that there's some mechanism that has, you know, roughly a time constant of x, and then we can choose if we want to make sure that we have a relaxation or retardation time constant rather that is there in one of our tau values. Okay, Okay, so let me just give you a definition here, though. The coefficients j sub I, okay, so the coefficients j sub I are called the Prony series coefficients, because what we have above is actually, this is a Prony series, equation 7 represents. All right, so a common way to model or specify viscoelastic behavior is to do it by giving a set of Prony series coefficients and corresponding relaxation times. So a common method, let's say, for modeling or describing viscoelastic behavior, okay, is by giving the Prony coefficients and the corresponding retardation times. Okay? So in the case, so if you're, let's say you're running Abacus, right? Since that's a pretty common FEA package. So if you're running this, you're trying to implement viscoelasticity in a finite element model. Abacus, for example, requires you to give it the Prony coefficients of the material that you want. So this is how Abacus expects you to define your viscoelastic material. Material to be defined. Okay, and then there's a corresponding question that comes up here, and that is how are you going to get these for a real material? So typically what you do is you actually have a real creep compliance curve, and then you're going to have to fit a set of you're going to have to fit equation 7 in some sort of a best fit fashion to that creep compliance curve. There's actually multiple proposed ways to do that, so there's not a single way that it's done. And I'll just make you aware that you should go. You're going to need to look up a methodology that you're going to apply to actually do the Prony series fitting. Okay, so we're not going to cover that in this class, but I need you to be aware of that. So if you do encounter this in anything that you come up with in the future, you know how to go about doing it. Okay, so these values, right, of ji and tau I, and even how many you choose, right, they are fitted, okay, to an experimental creep compliance curve. Okay, and I just want you to be aware that there are multiple methods to do this, and you just need to select one and do that. Okay, we're not going to cover that in this class. Okay, so that's how you would go about now taking an experimentally defined creep compliance curve. You'd fit it, you get these coefficients, and now you'd be able to go off potentially and solve some other problems for which you didn't do the testing for. Okay, we'll talk about how to do that more in future lectures.